All right. Hi, everyone. My name is Omer Zohar. And as Ezra mentioned, today I'm going to talk about a little bit of untraditional research that I've done, which combines two of my best interesting fields that I nowadays encounter, that is malware research, and especially malware infrastructure, and blockchain technologies, which I think is really cool and upcoming technologies. So how did I come up on this project? So a little bit about me. Sorry. So I'm a security researcher for the past decade or something. My main focus is malware infrastructure, CNC communication. I've always been fascinated on the problem of how malware communicate with the senders, and how exactly and what are the challenges in building a malicious infrastructure. I'm also a big fan of blockchain technologies. I've been in the blockchain, I think, 2013. And then after I quit my last job and as a head of research for Toxin Security, I had some time with my hands, and I thought this is a good time to do something that combine these two together. And I decided to check to see how they combine together. So yeah, so I also had a little bit more. A new member joined my team, so he helped a lot. So it's not all ideas here are exactly mine. And one last thing, I want to thank Amir Sagi, who helped me do this POC. The demo that you're going to see later is a lot of, he helped a lot on that. So what is malicious infrastructure? So let's understand that something that we generally disregard when you think about malware, it has a lot of backend behind it. So malicious infrastructure is supposed to help the malicious attacker to generate implants. He has to allow him to help him to deliver that implants to an unknown and very hostile environment. Then it have to be able to let him contact back to the sender and making the first contact, and then it has to provide facilities to receive, execute, and exfiltrate stuff, whatever it's nefarious stuff that he needs to do. It has to maintain control over time, or over long periods, and maybe disconnections and rough communication method, and provided depends on the use case, it has to allow mass control of multiple instances. And when you think about it, there is no one real method of doing that. There was a lot of trials over the years, and I compiled a list of what is, for me, what is the features of the ultimate infrastructure. So first of all, we have to have secure communication. So it has to be immune to data modification, eavesdropping, man in the middles, and stuff like that. It has to have high availability. So the node always have to find the command control and be able to communicate with it. It has to be scalable, so it can support any number of instances. It has to have authentication, so only valid implants can connect to the network, and no some researchers or the adversaries can mess around. Hello, can you hear me? Can you hear me as well? Okay, I'll speak from here. So it has to provide anonymity. So no info can be gained about the network operators if there's someone doing research in the network, so it can't reach to its operators. It has to provide, it has to have no data leakage. So which are the peers that are connected, which are what type of data is flowing over the network, what the commands, what the data is being infiltrated. It has to be takedown and takeover resistant, so no one can, again, take over the network and take over the botnet, or maybe take it down. And of course, lastly, it has to have low operational cost. So that eventually, especially for criminal activities, The cost is basically what determines the way of the operation. If they can make money out of it, they probably won't gonna do it. Okay, so almost all malware infrastructures that I encountered so far fail in one or more of these features. And I said, okay, let's see how blockchain as an infrastructure will be able to deal with this gap. And I looked at all of these features while I developed my POC. So let's see why I even bothered with blockchain in the first place. So I compiled here a list of, I'll try to summarize what is blockchain in one sentence. And I think it's a really nice one, but there is one guy that explains it much better than I do. So.
Blockchain technology allows a record or a ledger of every Bitcoin transaction ever made to be stored not in one place, but across vast numbers of computers. That is part of what people mean when they say Bitcoin is decentralized. And decentralization has a lot of theoretical advantages, from speed to security.
Okay, so I can't add anything more. That there's nothing. No one explains stuff better than John Oliver. So basically, what gave me the head start to start looking at blockchain is that the immutability and the decentralization, which is exactly what you need and what you want when you start this type of infrastructure. I chose to implement my POC on top of Ethereum. And again, I read from the Ethereum, the main website from the Ethereum webpage. Ethereum is a decentralized platform that runs smart contracts, applications that run exactly as programmed without any possibility of downtime, censorship, fraud, or third-party interference. So right out of this sentence, you can see that at least 3 of the features that I mentioned earlier holds here. Another cool feature of Ethereum is that it's very popular. It's the largest blockchain out there, yes, even more than Bitcoin in the terms of number of nodes. Last time I checked, it has more than 27,000 nodes that can run my code. The code is run on smart contracts, which is it's called the EVM, the Ethereum Virtual Machine, which basically allow me to run code on top of blockchain, and every one of those nodes will run my code. It provides encrypted communication. It has a dev peer-to-peer over RPLX. This is the protocol that they use. Same protocol that Cadmilia network used to use. If you know EMU from back in the day, it's the same, basically same peer-to-peer network. And it has the Ether, which is the crypto coin that drive the platform and basically give the incentive to put this network together. Okay. So let's connect the dot and see how this infrastructure would actually look like. So we have the network operator. He starts by running an Ethereum node. This node is a full node. It runs and it starts to sync with the blockchain. This is a heavy operation. It takes almost usually 24 hours. It takes a lot of RAM, and the last version, it's very heavy on the computer. It's very neat to have a really big system in order to run a full node nowadays. Once it syncs, the operator can generate its wallet that will control everything. He unlocks this wallet, and then once he has Ether in it, he can deploy the smart contract. A smart contract is basically the code that will run on top of the blockchain, and we do all the logic of our infrastructure. After all, he deploys the control panel. The control panel basically allows him to allow or revoke instance, issue commands to the bots, and fetch results and whatsoever. So every type of command that you can think of that a CNC is doing. And then he goes, once this is in place, the infrastructure is ready, and he can start generating the implants. So what it takes to generate the implant? It needs to create a wallet. It has to authorize the access in the contract. He has to transfer funds, and he has to pack it. Once this is done, so magic happens, which we'll not be discussing here today, and he delivers it into a remote machine. In the remote machine, the implant, again, it reads its configuration. It runs an Ethereum node. The Ethereum node runs in a light mode. This light mode is basically, it's not downloading the whole blockchain, it's just downloading the headers of the blockchain. So it takes a lot of less resources from the computer, around 300 megabytes of disk and a little bit of RAM. And once it's finished syncing, takes about 20 minutes. It can load its wallet that it was pre-implemented in the code, and it connects to the smart contract. It does the registration. It says to the contract, hello, I am this implant. I was registered, pre-registered ahead, and the smart contract allows him to connect. Once it's done, then we can start issue commands to the implants. So this is the overall infrastructure. Now, let's dive into the smart contract itself and see how it's implemented. Hopefully, you can see a little bit of the code that I wrote here. So this is basically my first attempt to run this contract. The smart contract are written in a language called Solidity. It's a nice language, basically it's a strictly typed language, which is similar in the syntax. It looks a bit like a hybrid between JavaScript and C. So this is my first attempt. It was very straightforward, the same way I code everything else. So do you have a little bit of structures and hash map that will do all the accounting, and you have a constructor down at the bottom that basically sets the sender, the owner of the contract. In a smart contract, every contract has an owner, and this owner can do privilege operations that gets determined on the constructor of the smart contract that runs only once. So, for example, a nice feature of the language is a modifier. A modifier allows me to define some preconditions to a function that I can check before the actual code is being run. So, for example, in a function like allow instance, I can say only by the owner. That means I can only call this function if I hold the owner's account. So this is a very important security measure in Solidity. And I can also say, for example, in a function called register instance, allow this registration to happen only if this instance was not already registered. Okay, so this is basically the contract. There's a few more functions, but this is basically it. So it's very simple. The problem is it doesn't work. And the reason it doesn't work is this return function over there. Anyone has an idea why this doesn't work? No? How many of you ever wrote in Solidity? One, okay. Two, all right, cool. All right, so I'll tell you, okay. So this is the call to the function register instance from the client, okay? So it's, so the result, after I call this function, in the regular programming method, you expect that the session ID here would be in the result over there. But when you program in a smart contract, this is not valid because when you call register instance, you actually issue a transaction on the blockchain. A transaction on the blockchain, A, it takes time, and B, it costs you Ether. And the reason it takes time is because when you change something on the blockchain, and in our case we change because we want to say this instance can be registered, so we have to wait for some miner to include this transaction in a block. This takes time, and until that we cannot see our changes on the blockchain. So what we get on this result is basically a transaction hash. This transaction hash can, once it's confirmed, we can see the details of this transaction. So how can we put out data from a smart contract? Every transaction hash is something called a log. A log basically lets us to emit logs from the transaction, and then by that we can, as you can see here, in the transaction log, we can see the data that emitted from the transaction. So what we can do in Solidity is there's another paradigm called event. Event basically allows us to define predefined events that, in this case, we trigger the instance and the session ID, and then instead of the return function, we just trigger this event, and then we look for it. Oops. Then we look for it on the, we look for it afterwards in the transaction hash. So now we have a contract that works. And this time, we need to ask the question, how much does it cost us? So every operation on the blockchain costs Ether. When you write smart contract, this is called gas. Every EVM assembly operation has its own price that is listed on the Ethereum yellow paper, and they update it from time to time. And the stuff that we're interested here is a function that is called SSStore, which is the function, the operation that stores data on the blockchain. And this is one of the most expensive operations that you can do in blockchain, which costs 20,000 gas. And then if you want to know how much it's costing Ether, well, the calculation is the transaction cost in Ether is gas times the gas price. Gas price is the transaction fee that you pay to the miners. So you pay, say, 4 gwei per 1 unit of gas. So you multiply them together. And it also determines how fast, how much incentive you give to the miners. So if you pay little gas price, little incentive, so there will, the confirmation time takes 3.5 minutes. If you want to double that or 10 times that, it can take around 30 seconds. This is roughly the times that on these days. So if we calculate the cost of writing one word, 32 bytes, it's roughly 2 cents. I took the measurements of $500 per Ether. That's the price yesterday. So if I want to write 1 megabyte, according to this calculation, it cost me $6,500, which is a lot of money to write to only 1 megabyte. So, and if you think about it, writing unbounded strings of data to the blockchain is not really a good idea because it costs a lot of money. But in our case, we don't really even need to write these strings to the blockchain. We just need to move them from the CNC to the implants. We don't really need to save them over on the blockchain. So fortunately, there is a cheaper way to do it, and this is exactly the event logs that I showed you earlier. So apparently, this cost, writing an event log cost only 68 gas for non-zero bytes. So in the calculation, writing 1 megabyte using a log event cost me only 1.4 Ether, which is 10 times less than what the previous method used. So let's fix our contract to do just that. So instead of all the accounting that I had before, I just write 4 types of events, and then I changed my functions to just, they basically do nothing right now. All they do is check the precondition and emit the event. Check the precondition and emit the event. This makes the smart contract very simple because all we are doing is take the data from one side and deliver it to the other side. And it simplifies the contract a lot, and it saves us a lot of money. Okay. So now that we have a contract that is working, let's talk about transparency. As I mentioned earlier, on the blockchain, everything you do is public. All the transactions are public. Everybody can see everything that you do. So how does this affect my infrastructure? So first of all, the contract bytecode is available for once you deploy the contract to the blockchain. Everybody can see the bytecode of the contract. It cannot be, you can't get around it. It has to be there so everybody can read and write it. The assembly of the EVM can be easily reversed, and there are also reversed, there are projects online that can actually turn it back into a Solidity code. So take into consideration that every smart contract you write can be easily read by everyone. And what about the storage? This is also can be easily read. So this is an API code that's from the Web3. Anybody can see, so for example, if I just put the smart contract and some index, and it will give me the value that is currently in the first defined variable. So in this case, this data here is the address of the owner of the contract. So this is the latest value of the data. What if I want to see previous or historic data? Everything is written on the blockchain. Blockchain is a blockchain. You can, all the history of all the transaction is written and available for you always. This is the big promise of blockchain. So if you want to see what it was the owner, like maybe 3 months ago, all you have to do is sync an Ethereum node to this point where this value was was correct, and you can see also all the historic data that used to be in every variable. So everything that you write into the blockchain can be easily maybe it's not that easy, but it can be, with a little bit of work, can be done. Function calls. Function calls is also transparent in the transaction data. Over here, this is the transaction identifier, which is the prefix of the SHA, of the signature function, and then you have the argument, which is the instance, address instance, and the command that I issued. This command is the add work command, so that give some command to one of the implants. So everybody can read whatever commands you give to the others. And finally, as I mentioned earlier, the log events, the data that you put out from the transaction can be also read from the transaction log. Okay, so what does it mean for me in my project? So currently, in the current implementation, we are leaking all the allowed implants, which implants can be allowed and which implants cannot, all the activated ones and on the session IDs, all the commands that I send and all the replies, basically all the data that flows on the network. And if you think about it, you can take it a little bit further. You can honeypot it. You can take the machine ID that I used and put the implants in another machine. And you can do a replay attacks and man in the middle. Basically, whatever you want, because everything is open. So this is not good. So let's fix that. And this is my final revision of the smart contract. Instead of writing everything in clear text, we're going to encrypt it. So all the addresses that are marked in red, all the address variables are marked in red, instead of writing them onto the blockchain as is, we hash them and write the hashes to the blockchain. And all the unbounded strings, we just use public key encryption in order to encrypt all the strings for the recipient. So we use the address, the public key address, for the instance that we want to send the data to. We encrypt it, and we know that only with the private key you can later decrypt it. And this basically solves all of the visibility problems. And finally, I want to talk about takeover and takedowns. So as I mentioned earlier, blockchain is immutable, and this is the basic inherently reason why it's secure to write stuff into it. Once you write it down to the blockchain, it cannot be ever changed. And again, I let this guy explain why.
We'll share a really helpful, really dumb metaphor for why it is safe.
The way I like to think of it is that a blockchain is a highly processed thing, sort of like a chicken McNugget. And if you wanted to hack it, it'd be like turning a chicken McNugget back into a chicken.
Okay, so this is a perfect metaphor for why blockchain. Well, the proof of work that the miners are solving when they validate blocks is exactly the reason why blockchain is safe. Because you need infinite, or at least more than 50% of the entire network's computing power in order to reverse a transaction. And this is exactly why I chose Ethereum, because it's a very big network. For example, if you go to a small network like we seen in Bitcoin Gold a few weeks ago, it can be done. But for Ethereum, probably in the near future, it will be probably safe. So if you write a smart contract, our own smart contract to the blockchain, we know that no one can take it down, unless you do a hard fork. And this was done once, when in an attack called the DAO attack. The Ethereum network was very young, and it was a very big, high-profile attack, and the Ethereum Foundation thought it would be a good idea to do a hard fork and reverse all these transactions. They got a very big, strong backlash from the community, and it's unlikely it will ever happen again in the near future, unless your botnet will probably take down the whole Ethereum network. So takedowns are probably non-feasible, unless you shoot yourself in the foot. So Solidity is a very nice language, but it allows you, like every programming language, allows you to shoot yourself in the foot in various ways. So, and almost all the breaches that you saw in the news that stole multiple millions of dollars from Ethereum's contract is due to not bugs in the Ethereum network, but on the smart contract itself, the DAO, the parity multisig, and actually there was a recent study conducted in February that do the static analysis of all smart contracts, or a lot of smart contracts deployed in the Ethereum network, and they found that a lot of them are susceptible to either takedown, or a takeover, or just stealing all the Ethereum in them. So, and it's all due to bugs and unsecure coding of the smart contract itself. And I'll give you a little example from my own POC that I did for this project. So, and this is a true story. So, as I mentioned earlier, I want to implement some kind of filter on the blockchain for the implants. So for event that is called command pending, basically the implant is waiting for commands from the CNC. So he's waiting on a specific event hash, okay, so this event, and it's waiting on its own. It listens to events to its own implant address. And it just sits there and waits for a blockchain to emit the event. So what can possibly go wrong with that? Let's say that we have an adversary. He deploys a contract called Evil CNC, and it has the exact same event signature as my own event. And then he do a function that is basically calling this event. Then he selects a function, he calls this add work function with my implant address, and he picks a command. In this case, I took the liberty of choosing a command that has a very long output, and it triggers it, sends it to the blockchain. Who can guess what will happen? Well, I won't keep you waiting. Well, of course, my implant will happily execute this transaction. And not only that, the implant will actually execute this function. This is a function that has a long output, and it will execute it and return the results, not to the evil CNC, because he doesn't know about it. He returns it to the original smart contract address. So not only did we cause the implants to spend a lot of ether because the transaction size is very, very big, we also can shove arbitrary data to the CNC itself. We can also use that with other commands to reveal what is the IP address and what is the location of the bots, and the possibilities are endless if, for example, you find some bug in the CNC itself. So this is a very big problem, and because we are in a security conference, it's not going to be a security conference talk unless I can name a vulnerability. So I called it the side contract attack. And the fix is, huh? Yeah. No, I didn't go that far because the fix is very, very easy. All you have to do is on the filter that the implant is listening to, you have to specify what is the contract address that you are listening on. This is very simple, but and very intuitive maybe, but almost all the code that I checked and all the examples that I've seen in all the different documents, no one's talking about it. So this is just an example of how a small mistake, disregard from the programmer, can cause catastrophic events. Okay. Let's move over to the final calculation of all the infrastructure. So I did some calculation. They're not very interesting, I think, of the round trip times of how much it costs to send this type of data and this type of data. Eventually, the average cost is roughly, per byte is roughly a few quarters of a cent. I did some estimation. If you, on average, you send 256 bytes on each direction 3 times a day, the annual cost of one bot is in today's prices is around $146, which accumulates to, if you have multiple bots, accumulates to a pretty hefty sum. If you compare it to, so for example, just a regular CNC that sits on some kind of bulletproof servers, of course, this cost is outrageous. And this is a very big problem. We're going to talk about it later on. So this basically covers all the stuff that I want to check, and I think now it's time for a little demo. The demo I did is a movie, because otherwise we would be sitting here waiting for transaction to confirm for a lot of time. So let's go through it. So first we start by running the node. We're generating an owner account, and then we start running the node and initialize the blockchain, syncing all the blockchain. And then once it's done, we unlocking the account and deploying the smart contracts onto the blockchain. Afterwards, once it's deployed, we're gonna load our CNC server. So we're loading the wallet and everything else, and afterwards, some magic happens, and we have our CNC. Okay, so now that the infrastructure is up, we can start generating the implants. So now we generate the implants, we generate in a wallet for the instance, and we wrap everything in one nice package. So, and you can see that we just registered the instance into the smart contract. Now we're gonna move the contract to another machine, and we're gonna run it. We run a local get node, and we wait for it to sync, and we load in the contract and the wallet from the implant configuration. You can see that we have an account balance of 1. This is the amount of Ether that I gave this implant. And you see that it's ready, and it's now waiting for work. Over on the left, you can see that the CNC has been informed that it has 1 instance running. Now we're going to issue some command, a net start command. You can see it start running on the side, on the implant side, and over on the CNC side, we have the data reach the CNC. Now we're going to do something fancier. We're going to generate another client. Let's generate it, and once it's synced, you see that it's already pending, and then in a bit it will be registered. And now we're going to do, just to show you that it can have multiple instances, we're going to issue another command. This time, we're going to just tell it to say what is your user, and run it. And you can see over the right that it's running on both ends. And we got it. And you can see that one says Alice and another one says Bob. So, thank you. Okay, so to sum it up, is blockchain the ultimate infrastructure for malicious activities? So let's go one by one. Secure communication, yeah, we got it. We have a state-of-the-art peer-to-peer network with thousands of nodes, fully encrypted wire protocol. So it's right out of here, it's a lot better than most CNCs nowadays. High availability, okay, as I mentioned, we have thousands of peers around the globe. So unless you block the whole Ethereum network, and the assumption here is that Ethereum gonna have some useful applications that a lot of organizations won't be gonna use, so they cannot really block the whole Ethereum network, because otherwise this application won't work either. So as I mentioned, we have thousands of peers. So and once you connect to one peer, all the other nodes are talking with each other and getting you all the other nodes. So all you have to have is one unblocked peer in order to connect. So this is very good. You can be sure that you're gonna find some node to connect to. Also, blockchain, as I mentioned, blockchain is immutable, so the contract can be modified once it's deployed. So once you deploy an implant with some contract address written into it, you can be sure that this contract will be there and it cannot be taken down. So it will be there, and you can contact the smart contract. Regarding scalability, so this is a problem. As I mentioned earlier, Ethereum today, the same as Bitcoin, all the large Bitcoin networks have a very big scalability issues. As you saw, it takes between 30 seconds to 3.5 minutes for a transaction to get mined. So obviously, this type of infrastructure is not suited for real-time stuff. If you're okay with sending command and you get the results after a few minutes, then it's fine. Another problem is that the implants are uniquely generated. So you have to have a wallet and ether in each one of these, in each one. So if you want to deliver in thousands, you have to be, each one of the samples have to be unique. The implant footprint itself, even though we use a light mode of Ethereum node, it still takes 300 megabytes of memory. It has a large footprint on it uses a little bit of CPU. It has a relatively large footprint on the remote machine. They're still working on it, and I mean, this is also a big problem, for example, in mobile with Ethereum, and I hope this is gonna be solved in the next year or so. Okay, so I give this half a credit. Regarding authentication, blockchain guarantees the implant's accounting to be correct. So whatever we add to the blockchain we are sure to be correct, and the registration process ties the implant to a specific machine. So hopefully it cannot be moved around or and mess around with. The control over the wallet generated and the session ID that we give each implant give us a protection from forgery and replay attacks and all sorts of this problem. So we can make sure that only the implants that we allowed can connect to the network. Regarding anonymity, okay, so there is no way to know the transaction, where the transaction was transmitted from. So each and every transaction have to be there's no way to know which implant triggered which transaction. So you cannot know from the location, for example, of an implant or which term node it emitted from. So our implants are really anonymized. And regarding the owner of the smart contract, so again, because there is no way to know who is behind the Ethereum wallet unless he's doing all sorts of shenanigans with changing cryptocurrencies and going to some cryptocurrencies, you will remain pretty anonymous. So we're good on this front. Regarding data leakage, so as I mentioned, blockchain is public, but the encryption that we implemented prevents anyone from basically knowing what's going on the smart contract. What I can say is that we take for granted that one implant can be cut somewhere and they get reversed. But the way we designed the POC is that the only thing that we'll get if they reverse some implant is the wallet address of this specific instance, but it will not get more information about the network, about the implants, about all the other stuff that are going on in the network. And this is exactly what we want. We cannot do anything about reverse engineering, but at least we can prevent the data leakage. Regarding takedowns, okay, as we said, there is no governing authority for Ethereum, at least that officially, and it cannot be killed. So we are takedown resistant. Thank you. And unless we have a very ugly bug in the code, there is also there is no problem with the takeover and stuff like that. Regarding operational cost, as I mentioned earlier, Ethereum is very expensive nowadays. It's still, even though it's almost been cut in half in the price, it's still it's not very cheap, and it's not going to be any better in the next upcoming days if you believe in it. So we can consider alternative change. I don't think they are viable yet. There is Cardano, Neo, EOS, and Ethereum Classic, and a lot more that also run smart contracts, and you can do the same thing over on other blockchain. The problem is they're not yet popular, and the level of security in this network is not as good as in the Ethereum. Another thing you need to consider, there is no flat cost. Every byte you deliver from in the network costs you Ether. So it's not like you set up a server somewhere and then all the traffic is free. Every byte you pay, and of course you have to deliver some amount of Ether in each and every one of the implants that you generate, so that if some implants get reversed or been cut or something like that, you lost this Ether. So regarding, and I think this is the main problem with this type of infrastructure, and I think this is the main reason why we haven't seen this gets very popular yet, is the matter of the cost. But I think that as we're going to have more and more platforms that gives you the ability to run smart contracts, this type of problem will probably be resolved. So mitigation, is it even possible? Well, as I mentioned earlier, you can just block the entire Ethereum network. As I mentioned, it's not very a viable solution. The other thing that we can think of is some kind of a blacklist of smart contract. This is something that is not yet exist in any other node. It will have to be specifically written. It can be a nice project for someone if you want to take it. It could be a nice project or even a startup. So if you have more ideas about mitigation, you can come talk to me later. Finally, all the code for the POC is being released today to the public. The repos gets released today. It's been made available in this address. The demo video is also there if you want to see it. Take a look at it. And generally, if you have any question, you can find me on Twitter, and you shoot me an email. That's it. If you have any questions or something, yeah. The smart contract is here on testnet, but you can. The POC supports private, testnet, or public, whatever you want. You can deploy it. Huh? Did you run it on the mainnet? Yes, but I'm not gonna release it on here. Any other questions? Okay, thank you very much.